Okay, hi everyone. Welcome to attend our OPTSys Optical Photonic Computing System Seminar series. And this is our fifth seminar. So our seminar will include 45 minutes presentation from the speaker and 10 to 15 minutes for Q&A. And we'll strictly manage time within 1 hour. And if you haven't registered our mail list, I highly recommend you scan a QR code so you can receive our emails for upcoming events in the future. And you can RSVP and have a calendar automatically created for you. And we also have select channels for networking and collaboration. We also have a YouTube channel. We have already posted all the past events, video recording if the speaker agrees. So feel free to share the recording with other people in case they cannot join online. There are some logistics. The events will be recorded. Thanks to Cunxi for agreeing. And we will post the video online and also the PDF slides later on our website and GitHub repo. So if you have any questions during the talk, you can either unmute yourself to ask if it's very quick questions, or you can put it in the chat box and I will moderate a Q&A session at the end. Okay. And we're very glad to invite our fifth speaker, Professor Cunxi Yu. Let me quickly give an introduction. Professor Cunxi Yu now is assistant professor at the University of Maryland, College Park. His research interests focus on novel algorithm systems and hardware designs for computing and security. Before joining University of Maryland, Cunxi was assistant professor with University of Utah and held postdoc at Cornell University. His work received many best paper awards and nominations, for example, from DAC 23, SB 27, TCAT 2018. He also received an NASA Career Award from 2021 and American Physical Society DLS Poster Award 2022. And Cunxi earned his PhD from UMass in 2017. Okay, without further ado, let's welcome Professor Cunxi Yu give us the talk. Yeah, the floor is yours now.
All right. Thanks for the very kind introduction. I assume you see the slides well?
Yes.
Okay, and the animation works, right?
Yeah, works.
Okay, good. Yeah. Thanks for organizing this event, and I know Jiaqi and Zhenqi are putting a lot of efforts, and I hope all the attendees and try to register and also advertise this event to a more broader audience and to help this community to grow up. Yeah, so today I'm going to just take the chance to introduce some of the works we have done on one type of optical neural networks. And since I came all the way from background on computer engineering, I actually work on EDA during my PhD study, and that's the only thing I know. But I want to show you how did I connect my research, my research background to optical computing, and what is the opportunity I saw during these research explorations. And I feel like it's exciting for people who are in computer engineering directions to look into these because there are really a lot of opportunities. Okay, thanks for all the sponsors who are supporting our research. So I quickly got into this, right? So there's really not a lot to say about why we need to build more efficient hardwares, but I wanted to show you this trend of how digital design has been evolving in the last 5 to 10 years in order to handle large-scale AI workloads. Okay, so there are a lot of things that standing in different regions, but if you take a look of this trend, right, you can see all of digital design are bounded by this frontier, which means if you want to increase the throughput, you have to increase the peak power, which is kind of exponentially correlated in this case. So that means for data center, you have to suffer for your power consumption in order to get the expected throughput, right? So what we want to explore about optics, like, because this is an optic system seminar, and we're saying, oh, do we have the chance to actually push the frontier that to offer extremely high throughput, but at the same time we can maintain relative small power consumptions. So that is the idea of why we want to explore optic in AI computing, at least for our research. Okay, but there are a lot of challenges. It's not that easy to just oh, I wanted to build up optical neural network. I want to build the hardware systems that can target different AI workload. Okay, so I'm going to show you 3 major challenges I have faced during our explorations. The first one I want to highlight is about cross-disciplinary domain knowledge requirement. Okay, so if you think about what is optical AI system or optical neural network, right? So it is optic and neural networks, right? So in order to pursue research in this direction, of course, you have to understand what is the basic, what are the basics of machine learning algorithm, backpropagation, how to train on neural networks, and how neural network topologies works, right? But since everything is working in the domain of optics, of course, you even need the knowledge of optics, okay? So the example here is showing a Fourier optic modeling, which is something we are going to focus on. But this is not the end of it, right? So it's already very challenging saying I have to know machine learning algorithm very well, and also have to know what is optics and how to do optic hardwares. It's already a lot of challenges, but it's not the end, right? So for example, if you want to really train bottom up from physics level all the way to application level in a large scale system, and it's going to require a lot of computation efforts, right? To make sure the training and inference or testing before you actually deploy on the optical hardware is efficient, you really need some skills of high performance programming. So this is something, the example is something we have explored about using CUDA to accelerate some of the optic kernels during training. Okay, so I'm going to talk that a little more in details. And something else is about, you also need to have the knowledge of doing a core design, because when you deploy, let's say building prototypes on optical systems, such showing here, we are doing a passive system on optical cable. There's a lot of like unexpected noise or fabrication errors from the device itself. So you have to really take the consideration of core design to make sure your system that works as expected. Okay, so I'm going to break down these things in our compiler design to show a little more detailed motivation examples. The second thing is about infrastructure. Okay, so if you think about building a digital accelerator for convolution neural network, and almost everybody know where to start. Let's say if you work on FPGA, and you know you can pick up Xilinx, Vitis, or you can work on Intel HIS, or if you want to work on an ASIC design, like to build up an accelerator, you know you can start with Verilog, you build, you compile all the way into a Genius design flow, or you can even use the open source tool flow such as OpenRoad. Okay, and it's even easier if you're just thinking about building a neural network. Okay, so and deploy on like general purpose computing platforms. So you can pick up PyTorch or TensorFlow, and you can even have the luxuries of further optimizing your performance using TVM. Okay, but if you think about building an optical neural network, so we don't really have such an infrastructure, right? So everything has to start from scratch, and that is not what we want, because you have very, very low productivity in that case. Okay, and the last challenge I want to talk about is there's going to be more miscorrelations than building a digital design. So we know in EDA, so we have multi-levels of abstractions, right? So you write Verilog is not directly correlated to the actual fabric kit that you work is going to be specific digital technologies, right? We know there are miscorrelations. However, if you get into optical computing, the miscorrelation or the gaps from your mathematical modeling to the actual hardwares is going to be even more significant. Okay, so we're going to see. So this is one of the examples we have seen in simulation, our simulation versus our experimental setup, exactly deployment, but you can see that there's massive differences. Okay, so we're going to talk about a few of our research directions, like from algorithm and infrastructure development, in order to address these 3 main challenges. Okay, so yeah, so this is what, so simply break it down is going to be, my talk is going to be programming infrastructure section, domain-specific algorithms, and also end-to-end design study from our programming model all the way to hardware evaluation. Okay, so the first thing I want to talk about is about optics modeling, right? So in order to make everything trainable, so we do all the training on digital platform, and our targeted optical AI hardware right now is an inference engine. Okay, and the first step we wanted to do is to make sure we have an entire differentiable optical modeling, because once everything is differentiable, you can just use whatever backpropagation algorithms or auto-diff engines that are available in PyTorch or TensorFlow to really maximize the use of those advanced technologies. Okay, so just a quick review of what is just start a comment. Oh, yes, that's from that. Yeah, so just a quick review of which type of optical neural network we work on. It's called diffractive neural networks, and I will do a very quick introductions of it, and also in comparison to conventional neural networks. Okay, so in diffractive optical neural network, or a diffractive neural network in short, so everything is done in terms of in light propagation. Okay, so your input is going to be encoded with light. For example, in this case, you can use intensities to represent a grayscale images for this mini data set. And unlike conventional neural networks that you're going to use dot product or matrix multiplications to form a convolution layer or density or Boolean layer, everything in these diffractive neural networks, the computation part are fully in light propagation. Okay, so that means the computation part consumes no energy at all. However, it doesn't mean that the system doesn't cause any energy at all, because you still need some of the laser in the front to do encoding, and also you need a detector at the output to read out the values. Okay, so so at the very end of the system, so it propagates from the input side to the output side, and the output is reading out the intensity of the light after you do all these light propagations. Okay, and basically at the end, everything is going to be converted back to real numbers, because you have measured that the intensity out. Okay, yeah, so that's the steps. And I wanted to just show a little bit of the modeling we did with this to help you understand how we make a differentiable model for this entire diffractive neural networks. Okay, so let me break this down, the main computation part. Okay, so don't get scared about this math, because if you don't understand this, it doesn't really matter. Okay, so so the first part is free space diffraction. Okay, so if you understand what is free space diffraction and understand Fourier modeling, you can see this is basically a final approximation. If you don't understand that, that is completely okay. So these formulation, these two-dimensional FFT, matrix multiplication, complex domain matrix multiplication, and inverse FFT is going to give you this approximation of diffraction function. Okay, which is light propagate in this way in terms of diffractions. Okay, and this is very important because FFT multiplication and inverse FFT are fully differentiable. So we will first have our light diffraction function as a differential model. Okay, and then right after diffraction, so the light after diffraction is going to go through this phase modulation layer. Okay, so the way we to model the output out of the light diffraction with this phase modulation process is to add a complex matrix multiplication, and the phase modulation is performed in the way of using this cosine and sine functions. Okay, and as you can see, cosine and sine, complex value and complex matrix multiplication are all differentiable. So this entire diffraction and the phase modulation, which is considered as one single layer in our neural network, in our targeted diffractive neural networks, is a fully differential model. Okay, so you have a layer in mathematical model that is approximation of the entire physical phenomenon that is fully differentiable. Okay, and more than that, you can see everything here, the functions are all tensorizable, because everything that matches like multi-dimension, if you have different batch size, and that also can be handled. That's very important because you can put this on GPU, okay, and maximize the performance of it. So if we simplify this entire model, right, so this math model, and you have this very compact diffraction and modulation model that is shown here, and you can just represent these diffractive optical neural networks using a very similar form like what we did in conventional neural networks. There's going to be a recursive layer applied. And I forgot to mention what is the trainable parameter. Okay, so the trainable parameter is what we have put on this phase modulation layer. Okay, So you can see the theta here is going to be the trainable parameter per pixel, but in the end, this entire n by n dimension phase modulation layer is going to be the trainable parameters. Okay, so assume that you define the first layer using theta 0 and so forth, and you will have exactly what I've shown here, which is almost looks like a MLP. Okay, but it's not, because everything is done in the once you put this on the hardware, everything is going to be done in terms of light propagation with diffractions and phase modulation. Okay, and the last step is going to get output, right? So if you take in the output of this 3 layers light propagation, you're going to get a complex values in at the end, right? So the way to get this intensity out is simply applying this function, so a squared plus b squared, and then you do a square root. And you can see this becomes a real value, and then this is where we're going to start doing our classification. So how do we do classification in this case? Since this is a minute, right? So we are going to treat these output 10 regions. So we're going to collect the mean energy or the mean intensity out of this region, and we use this value to do our argmax, just like a conventional neural networks. For example, if you got 0 region as the highest intensity region of all these 10 boxes, so that means the prediction is going to be class 0. Okay, so if I give you a different example, put a 1 there, your if the prediction is correct, you will get the highest intensity in this 1 region. Okay, and this is so this is how we propagate everything from input all the way to output and get the classification out. Okay, so during the kind of this very quick introductions of what is diffractive optical networks, we can actually break that down into 3 pieces in order to understand the implementation and also how this implementation from mathematical model and to the hardware implementation. Okay, so as you can see, you have to have laser and input encoding that handles the input part. You have detector and output reading that handles the output part, and you have to have components that handles the internal propagation, which is the computation part, to complete diffractive optical network buildup. Okay, and that brings us to this our very kind of straightforward implementation idea of a library, which is our infrastructures for designing these diffractive optical networks. Okay, so first of all, you have to have the basic physics kernels that handles laser encoding, laser modeling, input encoding, and also the basic functions to do a light propagation, such as diffractions and phase modulation. Okay, and we also introduce a very simple network container that is going to be very similar to PyTorch sequential, so that in such a way you can modify and explore different topologies of your design. So remember, we are not necessary to stick with a fully a single channel passive design. You can also do different topologies as you want. So we're going to show a few examples when we discuss about advanced studies. And so in order to really make sure we can handle a very wide varieties of diffractive neural networks, we have to think about how to optimize runtime. We have to make sure our model, our infrastructure have a very good modularization, since we want to do a more like design space exploration. Okay, differentiation we already discussed, since the entire physics model are differentiable, and we have all the models that are the entire training can be just done with whatever optimizers that are available in PyTorch or TensorFlow. Okay, and at the end, I'm going to talk about how we optimize the fidelities with core design methods in order to fit into a specific targeted hardware setup. Okay, yeah. So this is our website, and the paper is going to be presented at ASPAS, and we passed the artifact values. I'm going to show you a little more details about how to use that, but before that, okay. So I got a quick question. So for how many pixels will you put in the faceplate? And how to match the input. Okay, that's how to match the input size. So yeah, I actually have more data later on, but I can just give a quick idea on that. So the regular size we have tested on the faceplate is about 100 to 100 up to 500 to 500. So that is limited from to the hardware that we have. And the way, and note that minutes is only 28 by 28 in terms of pixels, right? So what we did is we enlarged the size to make sure it matches exactly as the face space size. That's a very good question. But yeah, so I have more specific examples later on. All right, so just a quick overview of what does light reach do, okay? So our idea is very simple. We want to really minimize the learning curves for people who had background in PyTorch or TensorFlow for training convolutional neural networks, but also have a very kind of straightforward or intuitive interface to kind of connect to diffractive optical networks. So just like what we did in PyTorch, so you want to first define your data. So in this case, when we start initialize our entire system, remember now we work in light property. We work on diffractive optical network, right? So the input is going to be represented in complex numbers. So the first step is going to prepare all the data that are in complex representation that matches whatever laser you have, whatever hardware that you have to do the encoding. Okay, and also very important is that this diffractive optical neural networks are very sensitive or kind of specific to a given wavelength. Okay, so you have to make sure you initialize your wavelengths for the entire system and also define what is diffraction distance you want to put into your hardware system. Okay, so I'm going to show you more specific examples later on. And the second step is very similar to what we do as PyTorch as well, is you're going to define your input laser, which is like connecting to your data loader, and also define a model. Okay, so you can just do just like a sequential container that in PyTorch you would just stack your layers up in your model, and then you define your forward function to say what is the topology I want to explore. Okay, and our training module is basically directly integrating with whatever optimizers that are available with PyTorch, because most of our implementations are based on PyTorch, and since our model are fully differentiable, so everything can be seamlessly integrated. Okay, so we also have this optimization on CUDA, so you can do a much faster training than using a CPU or non-optimized version of it. Okay, and the last step is going to do a deployment, and our deployment backend that supports two of the hardware setups we have explored. One is to directly map into a spatial modulator mapping, and the other one is going to be a 3D encoding, because 3D printing rendering, because we use 3D printers to print out face masks for a terahertz setup. I just got one quick question I'm going to mention to read that. So you mentioned that you can enlarge the images to match diffraction layer sizes. What if the image is super large, but the layer size is very small? Yeah, so that's a very good. It did. So the largest image size we have tried was about 500 pixels. So in that case, we can still handle that with our hardware. So that was a Place 365. But they also have HD images. We didn't try it, but yeah, so you can basically shrink or compress the image a little bit. And the second part of the question is, if you shrink that, are you going to lose accuracies? Of course, like if you have, but I mean, as shown in many of the conventional studies, compress the images and does not dramatically reduce the accuracies if you're doing a classification, right? So at least we don't explore, we don't see a lot of like HD image classifiers these days, but mostly they do a little bit of compression on the input. So I don't have a quantitative answer how much loss we will have, but yes, there will be some loss, but I don't think it's going to be significant. Yeah. Okay, so just a very quick review of what is the main layer API look like. What does that look like? So you're going to have a lot of inputs that you're going to configure, like pixel sizes is the face resolution, like how large is it, and you have to define your wavelengths or your phase functions. I'm going to show a little more later on, but something I want to there's a lot of details that you don't need to care about, but one thing I want to emphasize is we have provided a multiple kernels that you can fit your design into more range of basic wavelengths, right? So, and if you also have an integrated FDTD verification engine that you can just call FDTD to verify the gaps, right? Because for optical modeling is approximation. Like you do want to say how much differences between FDTD and this model. Okay. But yeah, so I want to show you a specific case study. Okay, so this is the hardware we have tried. So we have we worked on green laser, which is 532 nanometer, and the distance between every two input to the first layer or in between the layers or the layers to the output are all 11 inches. The reason why I put 11 inches because this is an optic table that fabricated in US, and yeah, it's inch based. So you will see a very weird number like 2794, and that is the distance in meter. Okay, and you put your wavelength, which is also in the unit of meter, and the pixel size is remember I show you there are many pixels in one of the phase layer, and this is the dimension for one of the pixels. So that would be 36 micron. Okay, and the resolution means you're going to have 100 by 100 per layer. Okay, so this is a very cheap hollow eye SLM that handles 1024 by 768. But we only use the center part because that is it's easier for calibration, but also is more accurate to configure. So the R regions have more variations. So this is more or less like a prototype. But what I want to show you is that if you're using a very different setup, so all you need to do is to change the numbers, right? Say if you work on different laser source, you change the wavelengths. If you want to work on different distance, or if you want to try different distances over your design, let's say I want to try 11 inches there, 7 inches. So everything can be configured very easily here, okay? And after you stacking everything in your sequential model, and you can just define your forward function, and you must feel this familiar because it's basically the same idea as what you do as a MLP or convolutional networks, right? So and you get the entire model compiled basically. Okay, and yeah, so the next step is going to just do the training, right? So this is very simple. So I'm going to show you one example since this is basically the same idea as training a convolutional neural networks. Okay. So after we got intensity out in the forward pass, right? So you're going to just do the loss functions that works for classification because everything now is back to real domain again. Okay, so this is how did we do the training. So for example, in this case, you're just going to do cross entropy, for example, and then you compare with and that is computed with the normalized intensity and your targeted labels. Okay, and if you work on different tasks, you just need to change the loss functions. And once you train the parameters, and you can just deploy to this hardware system like this. Okay, all right. So now it's the exciting part, right? So after we do the training, we want to see whether this works on the hardware, right? So in light reach, we also it's very important to understand why these things works. And we actually have this visualization to monitor all the light intensity changes during the propagation. Okay, so as you can see, the light is basically moving the intensity of the original encoding slowly into that targeted region. Okay, so we're supposed to get a 1 right there, but this is what we got at the first time we deployed. I said, no, this is not right because it's completely messed up, right? So there's no correlations at all, and there's no way you can identify this as a 1 day. So what is the reason? So that we want to analyze the system and find out the issues. Okay, and the first issue we find out is that in our model, in our mathematical model, we assume that the amplitude doesn't change. So it's a full phase modulation. It's a phase only mode in the SLM setup, okay, or in the diffracted layers. Okay, but when we analyze the properties of this SLM, so we find out the amplitude and the phase are changing simultaneously. So that's the first issue. So you have a coupled amp and phase responses in our hardware. So that is one layer of miscorrelation, right? And the second thing, so is that we have all these SIM bought from the same company, same manufacturer. We bought at the same time, and you can see they are all performed differently. Okay, so you can see this is the first one, second one, third, and the fourth SIMs. You can see the characterization result are some of those are quite significant different. Okay, so they are very, very different in the way that you add another layer of miscorrelations in your in between your mathematic model and your actual hardware deployment. Okay, so that's the second thing. So you have unique behaviors for each of the SIM. And the last thing is, if I want to work on very, very different setups, let's say I want to use 3D printers, I have to change the entire programming interface again. No, that's not the efficient way of doing it, right? So for example, in this case, the thickness of the material is going to be different phase change, basically. And how do we handle that? Okay, so I'm going to talk about the core design algorithm. So before that, I'm going to show how to read one of the questions, how to automatically learn the pooling regions on the output. Okay, yeah, so that's a good question. So this region is predefined. So this is defined by the user. So we defined that at the beginning of our system setup. And is there any guidance to that? So for now, we don't find a specific like a rule to do that. So what we did is like we even split them out. We also try to tie everything close to the center. Really didn't make a lot of difference. So we figure out to even split is a good idea because this kind of minimize the impact from the merriment noise. Because if you put things that are very close by, your detector have noises that you might just introduce more noises to the prediction result. Okay, so but yeah, so we do everything at the design phase. So we define everything there. Okay, so just quickly talk about this algorithm. So I want to break that down into single pixel diffractions that you can see the problems. Okay, so this is the original model, right? So when we do phase modulation, which is just we assume that there's no amp change, so everything is a 1 there, and theta is the trainable parameters, which is the phase change values, and this is a one device characterization we have done. So you can see amp and phase are changing simultaneously. So let's see what's the problem, right? So if we include this amp change into this equation, so you can see so 1 becomes some value that when you configure your phase to a different numbers, right? So that is going to be different because it's not going to be exactly the same as this one because you assume that amp doesn't change, right? So that's the first problem. The second, so for example, if you say you give 0.3 pi and your A is actually equal to 0.9 instead of 1. Right? Yeah. So the second problem is that the first problem is we are showing here is the coupled changes, right? The second one is all of these devices, like maybe every single pixel has a different behavior. So how we're going to handle that? So you are going to have I know I'm going to show you a little more about how this is handled, and it looks like a quantization, but how you're going to handle quantization for every single pixel. So just keep that in mind that in the worst case, every single pixel can work differently, like this. Okay, everybody they have a different characterization as I've shown in let me put that in like this. Okay, so so the way we want to solve this is to introduce a discrete trainable functions that can handle whatever just give me a two list of phase and amplitude response, and I can do a coupled modeling in the forward, because if the forward is fully differentiable backward, I don't need to care about that because it's just handled by autodiff engine, right? So the way we think about the problem is we introduce a trainable discrete parameter here, and that is doing a selection. Like say, if I choose the second value of my list, which in this case, amp and phase are coupled measurements that are already done, and my forward function handles both. First of all, the coupled issue, and second, you can just do any list on different any of the pixels, right, or per layer or per pixel wise. Okay, But there's a problem, right? So if you put discrete values, like this is going to be one hot, like 0, 1, 0, 0, 0, and this function is basically saying I'm going to get this function. I'm going to choose the second configuration in my list, in my characterization result. Okay, it's not differentiable, so we put in Gumbel softmax to make this differentiable. I'm going to skip these details. This is an algorithm that enable differentiation through discrete vectors. Okay, so what we have done is put another trainable layers there and sample through a Gumbel softmax and get into a one hot result, and that is used to do the forward function propagation. Okay, and remember, with Gumbel softmax, everything is going to be propagated, is backward enabled. Then you can do the training that is train this floating point weights. Okay, but the eventual deployment is going to be a specific value that you have selected in your hardware list, measurement list. Okay, so a list of measurements is all you need in this case. So I think I will skip this one. So we also discuss a little bit about how to do better training to fit into this modeling, because this is actually very, very sensitive for the training parameter tuning. So I will skip that, and if you're interested, you can look at these ICCAP papers. Okay, but yeah, so you can see this is something that you can handle with quantization training, but quantization training has quantization aware training has two issues. One, the regional quantization training does not aware of 2 pi period changes. Let's say 3 pi is equal to 1 pi. You are able to model that, but that is going to add another layer of complexities. So we have more discussions of why that doesn't really work. But more important thing I want to say is this is the function that we really need if you want to integrate this core design algorithm in your front end compiler with a very simple API. So if you think about what is exposed to the user, right? So if you're if you are a researcher who work on PCM, right, phase change materials, and you want to try, oh, does my device actually work in this kind of setups? And all you need to do is measure or test your PCM devices, get a list and put it there, and our framework is going to handle everything. Okay, so that is the idea that why we want to do a differentiable training on these. So yeah, so that's the exciting part, right? So how did we fix the problem of this miscorrelation? And the answer is yes. So remember we did, this is the propagation, right? So I was showing only a static image, but this is going to be more like a small video. You can see from simulation, we can see the intensity is moving slowly to that region, and we are getting correct prediction for this couple of digits. And the second row and third row are the experimental measurements we have done on that optical setup. Okay, we pick A4101, 108, so A4108, because this is my student, and she was living in this zip code. Okay, so that's why she picked this. And we also tested some of the others, just to show you quick examples that we can also handle different minutes. And yes, the idea is the same, basically intensity changes. Okay, and I was really motivating about the power consumption, right? So how much better we can do in the real world setup. Okay, so we actually did everything by a very comprehensive evaluation comparison. So on general purpose, we did GPU and CPU. No wonder that they're going to be much less efficient because they're not really designed for this edge acceleration. So that's why we added the edge TPU, which is from Google. We married with a USB power meter that's showing like power supply current, so we can get accurate power consumptions. And we also measured ours by accumulating every single components that are involved in our hardware, right? It's basically everything on the optical table, and we measure that in a total. So we're not just looking at, oh, this is the computation part, but down on the optics, so I claim how many X we are improving. Okay, so this is why we're not getting that extreme high numbers like what you see in other optic-related AI acceleration work. We only got about less than 2X, right? Less than 100. Because this is this is a passive, bulky system. It's not integrated, so that's why. But that's why it's not that efficient. But still, the prototype showing a very good amount of improvements. And currently we are working on a monolithic fabrication to integrate everything on the chip for this diffracted optical neural networks. Okay. So for more details, you can read our ASPLOS papers to see how did we measure the power. Okay. I think I'm running a little bit late to show you the capabilities of how our framework can generalize. So this is a terahertz setup that is completely done by Lightreach as well. We use a very cheap Amazon 3D printer, $500, and the lenses are probably $2 to $3 per bottle. And the thickness of this material is going to represent different phase change, right? So this is the laser side, and we do integrated 3D printing, so all the layers are connected with the sidewall, so it's easier for alignment. Okay, so and we got about 93% accuracy. Is not that high if you compare to digital system, but consider this is the terahertz. This is actually much harder to characterize, and we work on a 0.3 T frequency. Okay, but yeah, so the results are relatively good. So and also later on we did some other analysis. Is that if we find out if the layer are smoothed out, it's easier to do correlation. Like, so you get better correlation between your mathematical model and actual experiments. So we did a couple of work on the algorithmic part to do a smoothing that by using sparsity idea and also like some of the training tricks to smooth out the layers. Because you can see once you're done the printing, there are some of the surface are very, very smooth. Okay. Yeah, so I skipped this part, right? Because we did a lot of work on this to accelerate the kernels, because these kernels can be very slow. But I will just skip that. So another interesting idea I want to show is you can, since we have this model, right? This entire program infrastructure, it's very, very easy for you to explore different training method. Okay. For example, if you directly do on this is a segmentation task on cityscape dataset. So doing segmentations basically. And what we did is we borrowed the idea of skip connections in UNet, and we found out that actually generate a lot of improvements to optical neural networks in diffracted neural networks in terms of segmentation. So this is what we got, and this was the baseline. Okay, and all you need to do is just adding that plus x0, just like what you did in PyTorch. Okay, and we also did actually a real time by using this in a very simple autonomous driving scenario, which is indoor lane following. So the label, this is the ground truth we're targeting. This is what is produced by the DON. This is the lab. This is the driving map we have built indoor when we were at the University of Utah, and we do all the data collections and by ourselves. Okay, and at least it works. So by the way, so this is a train on right turn. Okay, and it does left turn automatically. We also try to do a little bit outdoor testing. So outdoor is a little more messy because you have more noise. For example, you have shadows, you have different colors, and in the winter you even have snow, right? So that is actually putting a lot of more impacts on our system. But at least for these very simple road is actually also identifying the edges quite well. Okay, so I think I'll skip this. You can also take this framework and do some adversarial analysis, right? So and it's mathematically sound, and there are specific physics phenomena that is corresponding to adversaries of light. Okay, so I will skip that, and if you're interested, you can take a look at our experimental study on laser photonic review in 2022 that we actually identify light adversaries in real world. Okay. So yeah, so I'm going to conclude my my talk. So the idea is really simple: is can we push the frontiers of optical computing, especially in the era of neural network or AI, from the computer engineering point of view? My quick conclusion is that yes, there's actually a big gap between computer engineering and optics, and there are a lot of things can be connected and collaborated. So what we have done with Lightreach is we really want to connect fundamental, like low-level physics out of it to a real-world system, and by simplify all the internals using this compilation and core design methodologies. Okay, and so we have done a lot of things with adversaries analysis, architecture explorations, and also we have some of the application-driven material analysis. We have another paper that are planning to be submitted to, I think, Science Advances soon about PCM fabrication guided by this framework. So, but yeah, so at the end, I want to show you we actually have this everything open source. We even provided a collab version. So if you don't want to set up on your local machine, it's okay. You can just click the link and you can compile everything just like what I show in this video. With only 10 iterations of training, probably like, I don't know how long this takes, about 5 minutes, like less than 5 minutes. So you can see the propagation, also the how your face layers will look like. So this is the face mask printed out, and yeah, so feel free to give it a try. So, and I also want to, if you are attending ASPOS, so Inje is going to do a presentation in this session. Okay. Yeah, just want to thank my team. So Inje is my first PhD student. Also, she's lead on this entire optical neural network research, and my collaborator, Dr. Bilu Gao from University of Utah, and his students Rian and Jichao are working on this. So Daniel is an undergrad student who work on this autonomous driving stuff with diffractive optical networks, and he is deciding his PhD offer to, I don't know, like MIT, Princeton, and Caltech, I think. And Miha went back to China. I think he's a professor in he's now a professor in Zhejiang University. And thank you. And that's it, the end of my talk. Yeah. Okay, so I already. Yeah, so I already got one question, so I want to quickly answer. I actually got two.
Yeah.
So for segmentation, do you use grayscale images or direct RGB? Oh yeah, that's a very good question. We compress into grayscale, and we also tried RGB. We find out RGB doesn't really help. So we can do both. If you do RGB, you will have you have to encode 3 times and converge the input together into one neural network. But what we have at least for this simple data set, like, because it's the cityscape, like we know that is relatively simple, doesn't really help. But yeah, so the example we show, I was showing in the slides is grayscale. So basically, we compress this image into grayscale and then do the prediction. Yeah.
Yeah. So that's
and
for input in multiple dimensions. Natural following is like, for example, for convolution, you have multiple output kernels, input channels. So does does DON support multiple channels?
No, for now, we don't support, we can do multi-channels. We have another, we had a paper on discussing multi-channel, but the reason why I didn't bring that into this this talk is later on we realized it's very, very costly to really implement that on optical hardware, especially when we start thinking about on-chip integrations. So I want to really, really make something that works, and we can, and also easy to fabricate. So you can do multi-channel, but it's going to be extremely costly. If one channel works, so why not just stick with one channel? Yeah.
Yeah.
So that is our idea. Yeah.
Yeah, let me go to the very beginning. So there's a question at the beginning. So for DON, there are usually gaps between units. I assume it's pixels, like the spatial light modulator. So does this have a big impact on the final results?
You mean the pixel size?
Yeah, for example, the slow spatial light modulator, each pixel will have some gap in between.
Oh yeah, yes. That is a very good question. So if you have a bigger gap, right, so your diffraction model will change because there are going to be light that through, and also there are interference. So what we have found out, we have to have the pixels that are relatively close. So the one we use, this device, so this hollow eye SLM, is actually the field is only 0.8. So that means it's 0.8 multiplied 0.8 inside a 1x1 dimension. So you already have a gap about 20%, I would say. But still, this actually matches very well with using this Fourier optical approximation. Yeah, but that's a very good question. So if you have
even for the faceplate, right? Even for the faceplate, you have the gap.
So yeah, so basically this gap, if you look at in between these two, yeah, if this gap is too big, this modeling is going to be less accurate. So you have to use a FDDD to correlate that. But most of the SM you bought on the market these days are not that. I mean, it's pretty good. So the one we bought is extremely cheap. This is only like $2,000. So it's probably this is probably the lowest priced as a. So we have another one like reflection based that is like a $15,000 per layer. So we have another setup that is intact. Yeah.
Right. Yeah. Typically for different pixels on the faceplate, probably insert some termination region. So avoid the interpixel crosstalk interference.
Yes. So we have another paper 23. I didn't get a chance to talk about that too. How did we handle interpixel crosstalk issues? So what we done is we do a more fine-grained partitions when we do Fourier approximation. So that is I think that was published in Optical Express or Optical Letter. Yeah. Yeah. So
another
I have,
question is how to solve the problem of zero-level diffraction? Presents a very strong base noise and makes the diffraction result difficult to distinguish.
That's a good question. So for now, we do everything in a black box. Like everything is blackout. Is we minimize as much as we can in our test bed basically. So so that's why we wanted to start exploring integrated. So you can have everything that are integrated. So you minimize the external noise in that case. So we are working on that. But remember, this is all about proof of concept, right? So everything is bulky prototype, basically. Yeah.
So does current light rate supports customized pixel response? For example, I can design some pixel with polarization wavelength dependent response. And we cannot use LUT to describe everything. It's huge LUT.
Okay.
It's a multi-dimensional LUT with high resolution, wavelength dependent, polarization dependent.
I think we can, but you have to modify. I mean, you can build on top of the existing code we have, and make sure that actually matches in your scenario. But it might not work if this Fourier approximation is too coarse grained that you lose the entire correlation. So you might not work. So in that scenario, yeah.
In that question, the two can be separated by superimposed diffraction grading, but only a certain distance, such as 25 centimeter, can make the two completely separated, and light intensity does not affect each other. This means the propagation distance should be at least greater than 25 centimeter. So, and if the accuracy is highest at 20 centimeter, the two cannot be tunable. So it's a conflict between the distance and the diffraction related issue, I guess.
Yeah, I'm reading these. It said if it's greater than 25% the accuracy. So the when you say accuracy, do you mean the correlation, like the accuracy of the approximation model? I think that was the question. And do cannot be tunable. I don't think this is the question. It's more like a comment. But yes, thanks for the comment, and I'm going to mark that down.
I think that's a conflict between the prediction accuracy versus the diffraction issues, right? You have an optimal distance z for your highest accuracy.
Yeah. So you have optimal distance for the strength of diffraction, that's for sure. But the accuracy, because eventually what you care about accuracy in this system is about the accuracy for prediction, right? So and the nice thing about putting this system on a neural network or AI application or machine learning application is that machine learning itself is approximation. So if you have some kind of miscorrelation, that's okay. And something we find out is actually sometimes noise is good. If especially when you start training complex data set, like the outdoor autonomous driving is one example. With noise exactly works better than without. So yeah, I think you are absolutely right on the optical part, but just think about in the scenario of ML, yeah, noise is sometimes even good, right? So it's not an issue.
Yeah. Another question is from me is like for super large kernel, Fourier domain convolution, initialization and reparameterization matters in optimization. Otherwise, the large kernel cannot find a good solution. So, is there any special initialization method supported from?
Yeah, very good question. So what we did is it's kind of strange. Like we tried a few random initialization methods for the parameter setup, like for the trainable parameters. We also try like some of the conventional like K-mean initialization. It turns out random initialization is the best, no matter what is the scale of your system. Yeah.
Yeah. And the skip connection is a very good, right? Skip connection is a very good initialization. You focus on the.
Oh yeah, yeah. For sure. Yeah. So but I think there are definitely more insights we can identify or to mine out from, like to bring the idea from a conventional ML community to these, but we just didn't have so much time to explore that for now. But yeah, I think there are more opportunities to further boost up the training part.
Yeah. The last question is asking about the transfer learning,
right? Yeah. So do you think can transfer learning be applied? Yes, we did that. It's actually working. So the good thing of this library infrastructure is we basically compress everything just like a convolutional neural network. So you can just grab it and integrate it with whatever algorithm outside that works. And you have to change a little bit, of course, because it's not in floating, right? So it's not in complex tensors. For example, that I'm going to quickly show you this. Yeah, so this is smoothing out. This smoothing out process is basically a sparsity optimization. So we maximize the sparsity so we can have more smooth layers in that case. So you can just grab a package, apply to this model, and I believe that will work for sure because we did transfer learning on different minutes. We didn't try more complicated examples, but that works actually well. Yeah. And also, I didn't get a chance to talk about this, but yeah, adversary studies. We basically grab a package outside and directly apply it with a specific physics meaning. But if you have any other questions, if you have any other question, please feel free to reach me out by emails, and you can easily find my email online. But yeah, thank you.
Yeah, thank you very much. We can have more offline discussion. So thanks everyone
for joining.
Okay.
I just have one quick question. Yes, very good question, and very good question, and I believe that is a very good direction. So can NERF be deployed on this? I think so. Yeah, and we are also very interested. If you have ideas, if you want to discuss about this, please send me an email. Okay, so we are actually interested into VR AR applications. Yeah.
Okay. Yeah. Thanks, Cunxi, for the great talk, especially the cool demos for your DLN. And
thanks for the invitation.
Everyone for joining, and welcome to subscribe our mail list for our future seminar events. And I think this concludes today's event. Okay, thank you very much. Thanks, Cunxi.
Bye-bye.
Okay, bye everyone.